Hello everyone. So in this video we are going to solve hill climbing algorithm, which is advent of code day 12 problem. But before solving this problem, if you have not subscribed to my channel, then please do. It really helps me keep motivated to make new videos. Currently I am seeing my subscriber as 506, but not seeing much improvement in that. Please do subscribe. Now let's move to the problem. So in this problem you will be given a set of a string in the matrix format, and you have to find from source, you have to reach from source to destination by following some rule. So for example, if you take this matrix, this character matrix as one graph, then here it is denoting, capital S is denoting source point and capital E is denoting destination point, and you have to reach from source to destination and calculate the distance uh, minimum distance minimum distance you can travel with the help of that criteria. Okay, so here are the criteria. So first criteria, so let me just write it down. So first criteria is, so minimum point in the graph will be A and maximum is Z. So you have to reach from A to Z. So Z is the highest point and A is the lowest point. Okay, now criteria is, you can travel from A to the similar height or similar height or plus one height, which means you can travel from A to B, B to C, or C to C, similarly for A to A, and then B. Yeah, this kind of operation you can perform, but you cannot travel from A to C directly, because the height difference between these two are 2, and here if you see, height difference between these two are 1, these two are 1, and these two are 0. Okay, so you can travel at most one. Similarly, you cannot move from higher to lower. See, the second rule is, you cannot move higher to lower, which means you cannot move from B to A. So this kind of rule we have to follow. So if you take this matrix as an example, so here if you see, our starting point is S and ending point is E. So what is the possibility we can take? So either we can move in this direction or this direction, because we have to start from A, right? Because our initial point, our starting point will be A. So we have two possibility, either we can take this path or this path. So for example, I am taking this path, so S to A. Now what can be our possibility? So if you see here, B, which one? This one, or again here you can see. So again there are two possibility, either this one or this one. So suppose if I take the above B part, right? So if I take above B part, then what can be the truth? Let me just clean this up first. So if you can see, here is A and again here is B, right? And B here as well. So if you can take this one, then you have not reached here, and you can similarly push that into like Q or some data structure. Then from here you have what many possibilities, either you can move here, and you don't have any other choice, because you cannot move from B to Q directly. So you reached here. Now what is the possibility you can move? So you cannot move to C to B, you cannot move C to R, you cannot move C to B, because you have already visited this path, right? Now you can either move to this one, so C to C is possible path. Now you reach to C, what is the possibility here? Again, you can reach from C to C or C to C, and you cannot go from C to S, and you cannot backtrack to the already visited path, right? So suppose if I take this one, then you are reached here, again you have this possibility, and similarly. So this kind of traversal we have to do. So you have noticed, right, we are performing some graph traversal algorithm, and which is basically here, because okay, so this is basically a BFS traversal we are currently performing on this graph. So, and once we perform some operation, we will be keep track of the total distance traveled. Okay, so that we can check if the distance, when we reach to the destination, we will compare the distances traveled by the different path. If that distance is minimum, then we will print that as an output. Okay, so let me just walk you through my code. So if I walk you through my code here, you can see I'm not clearing this up first. So let me just show you my. So first I have read input. So let me just show you my input. Here is my input. It is a character matrix. So I'm just converting this character matrix into the matrix. Okay, so I've taken this matrix as an array, and I'm this S and E is source and destination point index, and I'm taking this I to keep track of the current row. Okay, so I'm just reading input line by line. Here, if it is destination, then I'm taking what is the current row and what is the index of E in the current row. Okay, so that will be the destination point index, and this 0 is the current distance. Okay, so I'm initializing that current distance to 0. Similarly for source, if it is S is in current row, then mark row and column as I will be the row, and find the S value in the current line, which will be the column value, and initializing the distance and appending that current line into the matrix array. Okay, now let's move here. Here this is just I'm just calculating the total number of row and column. Similarly here I'm means setting I to 0, because I will be here means pointing to some point. So I'm not because I'm using I in this code, so I don't want I to be start from somewhere. Since we are using BFS here, so as I have told you, so I will start from S. I will append all the possible path in the queue, pick one path, and again append its all children path into the queue. So for example, let me just walk you through again. So if I take this one as an example, okay, so here if you see, so initially our S will be in the queue. So suppose suppose I will initialize visited, so 0 comma 0 will be in the queue for this example. Visited set. Now what is the possible path? So either we can move this path or this path. So for example, the next path will be the, I will add that into the queue. So this one will also in the queue, 0 comma 0. Pop this into the queue and find the all path possible for all children of the current path, the current source. So all children of the current source is A and B, which is satisfying our criteria, right? So I will add both of these two into the queue again. Again, I will find pick any other child and add all its child to the queue. Same thing we are doing here. So that is basically a BFS traversal. Okay. So let me just clean this up first. Okay. Okay, so that we are doing here. So this one we are using for this part 2 problem. So I will explain you it later. Let me just explain you the BFS part first. So if you see here, I'm passing the source S as a list, because I just want to generalize this BFS function, so that this function can be reused in both part 1 and part 2. So here I'm just adding all the sources to queue, as I have told you, which is necessary in the BFS, and adding the same for visited set. Now this is the direction, because our direction will be so we are allowed to move in only 4 direction, either left, right, up and down. These 4 direction we can move. So that's why we have defined this list here, right? Similarly, if you see here, so I'm just looping through the queue, because while queue is not empty, just pop the first element from the queue and check, get the current value. So current value will be, since matrix will be in the tuple format, so 0th index will be in tuple format, which is the source array index, index, and second value will be the distance. So this is, I'm just finding the current value. I'm checking if the current value is destination value, then just print that distance. So current of 1 will be the distance, right? And return it. Otherwise, if current value is source, then mark it as A, because as I have told you, a source will be we have to start from the lowest point, which is the A point, and reach to the Z point. So that's why I'm doing it here. Now I'm just iterating through all the direction possible. So direction array here, if you see, let me just clean this up first. Okay, so if you see here, direction array here, so I'm just looping through that direction and calculating the new direction by adding the adding this value, current index value, to direction value. Okay, so this will be run, or this will check in all 4 directions. Here I am checking if outbound, means if current index is out of bound. If it is out of bound, then check for the next index, and just checking if current element is E. If its current element is E, then make it as Z. So that we are doing here. So if we found current element is E, then we are just sure that this is the highest point possible where we have to reach. This is the destination point. That's why we are making it as Z. Now we are checking if the current index which we calculated is already visited. So that we have told you. So this is just to check if to make sure that we don't visit already visited items. And here this formula, this one is to check if current element is either one greater, means plus one more height, or the same index height. Okay, so for example, here if you see, if it is the same height, then it will allow. If it is plus one height, then also it will allow. If it is more than that, then it will not add, or it will not visit that set. So that we are doing here. And so this is it. So this is the BFS we have written. So if you know the BFS, then you will definitely get this code. Now at the end, I'm just so here we were printing the value if we reach to the end of the if we reach to the destination. So that we are doing for the part 1, and this will work for the part 1. Now let's move to the part 2. So just in the part 2, what it is saying, any square at the elevation A. So it is saying that you can start at any point present in the matrix. So here if you see any point, so A will be the starting point, right? Previously in the part 1 we were taking capital S as a starting point. Here it is saying you can take any A or capital S as a starting point, and you have to find the minimum distance which you can travel. So here if you see, so there are lots and lots of A possible. So we have to take any A and any A and capital S and find the minimum distance which we can travel, right? So that for that we have written this function, find all lowest point. So this will give me the all lowest points. So lowest point is a small a or capital S. So if it is a small a or capital S, then yield the current index, and we will append that into the start position. Here we will append that into the start position. We will so a start position will be now pointing to all the lowest point which is available in the matrix, and we will run BFS on all of that lowest point. So this code will also work for the part 2. So if I show you the output, so let me just first show you the output for part 1. Just say day 12. So this one is output for part 1, which is 462. So if you check, 462 is the output for part 1. Let me just comment it out, because we are using same matrix, and so it will try to modify the existing. So I have to comment that out. Now let me just check for the part 2. So if you check part 2, 451 we are getting. So 451 is for part 2. So this is working fine as expected. Our code means this problem was only based on the DFS algorithm. You can think about using a DFS if you want. You can definitely try DFS as well. Thank you so much for watching. Please like and subscribe to my channel. It really helps me keep motivated to make new videos. Thank you so much.